So we were right here. If you have any questions, please let me know. Okay. So now we're going to move forward and let's start off with the definition of elastic limit. Okay. So elastic limit is a point beyond which the material does not return to its original alright signal to its original shape, and it is permanently deformed. And when something is permanently deformed, basically we called it as a plastic deformation. I'll just show you now. So generally it looks like this. You got extension on this side, you got force or load on this side, and then when you extend something too much, the first point is P, I'll explain what that is, and then it is elastic limit. So P is the limit of proportionality, so it comes always first, and then comes elastic limit, and beyond this it does not return to its original shape, like that. Now alright, now so basically then we can actually either it's like force and extension graph, and we know where exactly is the limit of proportionality. So now we can actually go towards the strain energy. Strain energy is basically elastic potential energy. Okay, so this is what strain energy means. Both are the same thing. So elastic potential or strain energy is the energy stored in a body due to change in shape, and it helps us basically that shape to recover. Okay. So suppose we have like force, newtons here, x in meters here. So the graph looks like this, suppose. Oh no. Wait a second, please. Suppose like this. And then, of course, it's going to turn like this, right? So it starts turning, right? So just underneath that, this is where we got to find the elastic potential energy. Okay, underneath that triangle. So now just check this out, please. So this is the elastic limit here. So area under the graph would be the strain energy here, and the strain energy can be calculated by half times this force times the extension that it has caused, because it's a triangle, right? So generally, when you have this formula done, you already know that since F is equal to kx, so we can actually replace this F right here. So the other formula for strain energy, which is widely used, is half times kx times x will be half kx square.
Will we calculate K over here?
From this graph?
Yes, sir.
Yes, you can do it. You can do it by taking the change, right? K can be calculated by just taking the gradient here, you know. So what I'm saying is that for elastic potential energy or strain energy, there are always two formulas. So there's like half Fx, that's one, and the other formula for this is basically half kx square. K is generally either they will give you in the question, or you can do it from the gradient from of the graph. Okay, is it clear?
Yes, sir.
All right, now. So suppose there is a question like this. It says a spring has a spring constant 65 Newton meters and elastically extended by 1.2 centimeters. Calculate the strain energy stored in the spring. Okay, now so this basically is pretty simple. All you need to do is you have the spring constant, you have the extension. So to find the strain energy, elastic potential energy would be half times k times x square. So half times 65, because this is in Newton meters, we got to convert this, right? So we convert this into 1 by 2 times 10 raised to minus 2 whole square, because we want it to be in meters. Okay. So basically, if you calculate this, then you'd realize that this would be somewhat like 4.7 times 10 raised to a minus 3 joules, like that. Is it clear? Any questions here? Okay, now the most important thing that I'm going to tell you is in these questions, you would be able to find change in elastic potential energy. So suppose they have given you a question like this, okay, and it's F and it's X in meters, and the line basically goes like this, and they say the spring constant on this one is equal to K. So you gotta find the change in energy between any 2 points like x1 and x2, like that. So basically what they want is they want you to find this change. Okay, so to find this change, what you should remember is, and I'm just telling you this very, very important lesson. So there is a correct way and there is a wrong way. So the correct way and the wrong way here, especially when you're using the equation kx square. Now check this out, please. So basically, to find the change in energy, you would want to subtract energy 2 from energy 1, and that would mean that this section as a whole, the green one, shows you energy 2, and only this section, purple one, is energy 1. So when you subtract both of them, you're gonna get the blue one. So what you're gonna do is you're gonna say this would be half times k x2 whole square minus half times k x1 whole square. By doing this, when you basically take half and k common, so you get x2 whole square minus x1 whole square, and that would give you the change in energy. But what some people basically do is they find change in x by doing x2 minus x1, and when they put it in this formula and they think, okay, I can put it as k x2 minus x1 whole square because it's half kx squared. So this formula and that formula are basically entirely different functions, which means that it would give you a very, very wrong answer. Is it clear, everybody? Do you guys understand this? Hamad, Aman, Aisha, everything is clear here? Javeria?
Yes, sir.
Yes.
Okay, that's very good. Alright. Now, speaking of that, then, let's talk about a question. Let's look at a question here. Wait a second, I just need to copy this. And this is a very, very important question because I think it's a tough one. I'm just pasting it up. It's taking time. Okay, this question. In this question, it says when a trolley is in equilibrium, each spring is extended by 4.5 centimeter. Each spring has a spring constant of 16 Newton per centimeter. The trolley is moved a distance of 1.5 along the direction of the spring. This causes extension of one of the springs to increase and extension of other to decrease. Okay. The trolley is released when it reaches highest speed. Calculate that speed. Okay. So that's what it means. So let's talk about it this way. So what really is happening here is that the trolley was right in the middle first, and each spring was already extended by, so extension in this one, let's call this x1, was 4.5. Extension in x2 was 4.5 as well. Is it clear, everybody? That's what it means really. Now, so suppose if it's further extended or moved towards one side, so the trolley basically moves here, and now one of this basically is less extended and one is more. Let's move this way. That would mean actually that x2 will basically extend by, it was already extended 4.5 and now you extend 1.5 more, so it's gonna be 6.0 centimeters. And on this side x1, now the new length of this is going to be 4.5, it was there already, minus 1.5 because it's like decrease in length, so it's going to be 3.0 centimeters. Do you guys understand this? Okay, now let's look at first of all the spring on the right side. Okay, so if I look at the spring on the right side, the energy that it stores, we know that it is equal to half times k times x2 square minus x1 square, and that's what we learned just now. So half times the spring constant is 16, and because the spring constant was 16 Newton per, oh, okay, I think we should change this. We should change this to meters actually. Okay, I'll change it to meters. So if I want to change it, change 16 Newton per centimeter to meters, so that would be like this: 16 Newton per centimeter. So if I change centimeter to meter, it would be 1 upon, or 10 raised to a minus 2 meters. So it will go up. So it is going to be 1600 Newton meter, like that. So let's call this 1600. And then the extension afterwards was 6 centimeter, which means 0.06 whole square, minus the extension before this was 0.045 whole square. So this is what I get, right, in extending this spring. So then it is going to be, let's take out the calculator and let's try to find this out. 0.5 0.5 times 1600 times 0.06 square minus 0.045 square, and that's basically 1.26 joules. Then we're going to look at the spring on the left, and that's energy equals to half times k times x2 square minus x1 square. So what you're going to do is, this will be 1600, this will be basically, final was 0.03 because it was 3 centimeter after it was extended, whole square minus 0.045 whole square, like that, right? So let me just change the color a bit. Okay, so then you put it into the calculator again. This time we can just change this value, and that basically gives us something like minus 0.9. Okay, so then what you're going to do is, because you want to find the change in energy, so total energy, so now the total energy of the system is gonna be the energy in the first spring plus the energy in the second spring, which is 1.26 plus minus 0.9, so that's gonna be 0.36 joules. Is it clear? Any questions? Okay, now what they want is that this is when it had basically accumulated this much of energy, and when it was released, it went like, it moved, and it would move because then elastic potential energy is going to change into kinetic energy. So elastic potential energy changes to kinetic. Now we have elastic potential energy as 0.36, which is equal to half times m times v square. So 0.36 half times, the mass is already given, that is 850 grams. So that could be changed to 0.850 kg times v square, because we need the speed. So ultimately, the speed is going to be equal to 0.92 meters per second, and that's the highest speed that's gonna gain. Is it clear, everybody? Any questions? Let me know. So remember this very, very important fact, and that is that the whole thing basically depends on this whole thing depends on whether you're using the right equation or not. If you don't use the right equation and you subtract x before you actually put it in the equation, it will always get you the wrong answer. So that's how it's done. Okay, Hamad, everything is clear? Anything you want to ask? Please go ahead.
Yeah, it's clear.
Okay, so now let's move to the next thing. Now there's something called stress. Now stress has a simple definition. It is called force applied per unit area. So you might have heard this before in pressure, but for materials, we use this tau sign for stress, and the formula for stress is that stress equals to force over area. Naturally, because it resonates with pressure, it is pressure really, so the SI units are going to be pascals, or simply Newton per meter square, that you can write. Okay. Now, there could be two types of stress in this. Number one, so suppose there's a material like this, maybe a cylinder, and then you're actually applying a force on the cylinder on either side like that. Because the cylinder is going to extend, we would call this sort of force or stress as tensile stress. The other way around is that if this same cylinder was pushed inwards like this and like that, then it would be something called compressive stress. So because there is a compression force acting on this, right? So you got to remember that. Okay. Now, there is a special case where an object may undergo both compressive and tensile stress. And that case is a beam. It's basically a structural member. I'll just show you that. May undergo compressive and tensile stress at the same time. Okay, in 10 minutes, please rejoin the link. Okay, now, so a beam basically looks like this. It's sort of it basically holds it's between columns to divide load. So if you apply force, I'm just making an exaggerated drawing. If you apply force on a beam from top, the beam would deform like this. Okay, because you're applying a force right here from the top. So what happens is that on the top side, the particles are basically forced inwards like this, and that's where the compression occurs. Whereas in the outer side, the particles are pushed outwards, and that's where tension occurs. So you got to remember that, okay? Generally, these members are made from concrete. And I just want to tell you that as a materials perspective, usually in construction we use concrete and steel. So concrete is strong under compression, it doesn't give in compression, and very weak under tension. So that's a property of concrete. Steel is strong under both compression and tension. And that is the reason that when buildings are made, so you might have seen that before they fill in concrete, they put steel bars at the bottom of that particular member, whether it's the roof, ceiling, or it's the or whether it's just the beam or something like that. So these are the steel bars, and then concrete is poured in to protect concrete from breaking. under tension, which the steel bars can hold. Is it clear, everybody? Any questions? Interesting. Okay. Now, so then comes strain. Now, strain is basically the ratio of change in length x over the original length, because it is just a ratio between length and length. So what you're gonna say is that, first of all, the symbol of strain is E, small e, and the SI units are basically none, because it's just a ratio, so meter or meter or centimeter just cancels out. The formula for strain is that strain is equal to x upon L. Okay. Sometimes the strain is also given in percentage. So percentage strain would mean x upon L times 100%. Okay. That's what it is. All right. Now, the next thing we're going to do is basically the Young's modulus. And Young's modulus is basically a very simple definition, really. It's a ratio of stress over strain. The symbol of Young modulus is capital E, and the formula then will be E is equal to stress over strain. We can further expand this by saying stress is force over area and it's divided by extension over original length. So area will multiply down and L will go up, which means Young modulus can also be written as F times L over A times X. Mostly this formula will be used. The SI units, because it is stress over strain, stress is pascals and strain has none. So SI units of Young modulus is also pascals. And the most important thing is that Young modulus, note here that it is a unique value for each material. So for iron it will be different, for steel it will be different, concrete, plastic, wood, everything it will be different for each material. Alright, any questions please? Javeria, Aisha, Aman, Aman?
Yes, sir.
Okay. You guys understand, right? No, this is just
Yes, sir.
yeah, okay. Very good, very good, very good, very good. Now, they might ask you basically some or more part of an experiment to find Young's modulus. So you're going to write that experiment. Experiment to find Young's modulus. Okay, so basically what you need is, so on the table, generally you would be doing it in your probably in your labs. So on a table like that. Okay. So first of all, you would want a block of wood, and on that block of wood, you also need a pulley, and then over that pulley, you gotta put a wire that basically just goes like this. Okay. Here you have mass hanger. Okay. And to stop the wire from slipping, what you do is you use a G clamp. So you see that, or you might have seen a G clamp in the laboratory like this. Attached to this, what you do is you also okay.
Okay. Yeah. Yeah.
So so attached to this, I just want to tell you, you also need a ruler. And ruler is like placed right here. And I now just label it. So this would be the G clamp. Block of wood. That's the wire that we're looking at. This is the ruler. That is the table. That's friction less pulley. And that's the mass hanger. Mass hanger to increase the weight by putting, we just keep on putting like weight on it. Also, at one point, we just put a tag. These are the tag, and when you add masses to this spring mass hanger, the wire extends. So the tag basically moves to a new location. So we know extension is cost. Okay, like that. So we need some list of apparatus in this. First of all, we need a ruler that is fixed. Then we need a micrometer screw gauge, and we also need slotted masses. Okay, let me just put it on the other side just to explain it to you what they're used for right here. So the ruler is basically used to find the change in length x at each addition of mass that you're putting in the mass anchor, micrometer screw gauge to measure diameter of wire, and you can simply find the area by using pi by 4 d square. That's the formula to find area of a circular cross-sectional wire. And the slotted masses to increment the force of tension. So you keep on adding the masses and it would increase the amount of tension that there is. So when you're basically done with this, you set it up and then you keep on doing this. So you take number of values. In your course, minimum of 6 values are generally taken. Sometimes 5 as well, so it's okay. So you need serial number. You need, see, mass in kg. You need weight, which can be found by mg, that's also in newtons. Then you need the diameter in meters, and then you need area in meter square. Then basically you need stress in pascals, and you need strain. So strain can be found out by change in length, right? And over original length, stress can be found out by weight divided by area, like that. So what you're going to do next is, the method to do this is that find the original length. Original length basically means that when there is no mass added, then what you're going to do is find the diameter and use area equals to pi by 4 d square to find area. Number 3, using stress equals to force over area for each increment in mass, find the stress. Number 4, using strain equals to x upon L for each change in length, note it from ruler, find strain. And then finally plot a graph of best fit from origin, because this graph will always start from origin, of stress versus strain, like that. So when you look at the stress and strain graph, you got stress on this side in pascals, you got strain on this side, no units really. So the line would basically look like this. Generally it shows you a trend like this, okay? So till this point where the straight line is, you just need to find the gradient. So the gradient of the graph is going to give you stress over strain, and that's what gives you Young's modulus. Is it clear? Aman, Javeria, Hamad, anything you want to ask now?
No, sir.
Okay, very good. So then I will see you people in the next class, okay, next week, inshallah. And let's complete this chapter then. Okay, bye. Have a nice day.
No, sir.